In the previous sessions, we considered some important discrete random variables. And now we'd like to see some more of them come up in important circumstances. So the first of these is the negative binomial random variable. Okay, so that we'll derive it, or we'll come to it via an application. Okay, so you have a machine that makes widgets one after another. 80% of the time the widget works, 20% of the time the widget is defective. The success or failure of producing a widget is independent of the success or failures of the previously produced widgets. Okay, so what's the probability of getting 5 working widgets from the 7 that are produced? Okay, so we've already done this problem, right? We need to what's the probability of getting 5 in a row that work and then 2 in a row that don't work? 0.8 to the 5 times 0.2 to the 7. That's the probability of that sequence because of independence. Now, if we don't care about the order, then how many ways are there of doing this? Well, there are 7 choose 5 ways of choosing where to put your successes, or 7 choose 2 ways of choosing where to put your failures. They're both the same, of course. And so the result is 7 choose 5 or 7 choose 2 times 0.8 to the 5, 0.2 to the 2. So 5 successes out of 7 trials. We've already seen that. Okay. Now let's change the question a little bit. What's the probability of the 5th working widget occurring on the 7th attempt? Okay, so that's a little bit different. That means that on the 7th attempt, you definitely have a success. And then in 6 attempts, you have to do you have to arrange for 4 successes. So what would that be? Okay, so you break the problem down. There are 4 successes over 6 trials, then a success on the 7th trial. Okay, so independent things are happening, right? Remember, we've said that widget success or failure is independent of previous success or failure, which means that the probabilities can be multiplied. Okay, so think of 2 things happening. So the probability of the first event times the probability of the second event. The first event is 4 successes in 6 attempts. And the second event is a success. Okay. So 4 successes in 6 events, so 6 choose 4 ways of doing that, times 0.8 to the 4, 0.2 to the 2. That's like what we've done before. Times, now that's the probability of the first event, 4 successes in 6 attempts. And then the probability of a success in the 7th attempt, we said is 80%. Okay, so note that that's 7 minus 1, choose 5 minus 1, times 0.8 to the 5, 0.2 to the 2. Okay, now let's just generalize. Let's say that the probability of success is P, and the probability of failure is Q is equal to 1 minus P. What's the probability that the 5th success occurs on the 7th trial? Well, replace, as in our previous result, replace 0.8 by P and 0.2 by Q. Okay. And then you get 7 minus 1, choose 5 minus 1. Right, you have 6 trials in which you have to place 4 successes. So there's 7 minus 1, choose 5 minus 1 ways of doing that. And then you're going to get 5 successes with probability P and 2 failures with probability Q. So 7 minus 1 choose 5 minus 1, P to the 5, Q to the 2. Okay. Now let's generalize again. What's the probability that the 5th success occurs on the Xth trial, on trial number X? Okay, so what does that mean? It means that in X minus 1 trials, you have to have 4 successes. And then on the on trial number X, you have to have a success. You have to have that final 5th success. Okay, so 5 minus 1 successes in X minus 1 Bernoulli trials, then a success in trial number X. Okay, so how many ways to in X minus 1 trials, you have to place 5 minus 1 successes. So the number of ways of doing that is X minus 1 choose 5 minus 1. The number of successes that you need is 4. So that's P to the 4 and then Q to the X minus 5. There are X minus 5 trials left. And then you multiply once again by P. That's the probability of that 5th success. Right. So it's X minus 1 choose 5 minus 1, P to the 5, Q to the X minus 5. Now let's generalize again. We'll say that we've got instead of the 5th success occurring in trial 5, we're going to have the kth success occurring in trial X. And so what you get, you just replace the 5 by K, you're going to get X minus 1 choose K minus 1 times P to the K minus 1 Q to the X minus K. Okay, so basically that is that's the PMF for the negative binomial random variable. Remember, we are using well, okay, so then you have to multiply by P again for the final success. And then you would get X minus 1 choose K minus 1 times P to the K Q to the X minus K. Okay. Once again, remember the assumptions here: independence of the trial, success and failure in different trials, and these P and Q are not changing from trial to trial. Okay, so we've worked out the negative binomial random variable. Right, so summing up, we have repeated independent Bernoulli trials, which result in either success or failure. There's a constant probability of success P and a constant probability of failure Q equals 1 minus P. X is the trial on which the kth success occurs. Okay, so that's the distribution. And if you do a bit of work, you can get that the expectation of the negative binomial random variable is equal to K over P, and its variance is KQ over P squared. Okay, so let's take a problem from Walpole. Scientist needs to induce a disease in 2 lab rats. The probability of contracting the disease in each trial is 1 over 6. What's the probability that 8 lab rats are required? So one possibility is that 2 are required, right? You got a success on the first one, you induced the disease. You got a success on the second one, you induced the disease. Only 2 are required. in principle, this could never finish. You just never got any of them to get the disease. You just keep going through lab rats. Probably not going to happen. And you could have something where 8 lab rats are required. What that means is that in 7 trials, you got you got 1 success, and then on the eighth trial, the 8th rat, you got your 2nd success, and now you can stop. Okay. So, what's the probability that you could do that? Well, we want to have an idea of how many lab rats to order, right? We have to import these from Norway or something. So we want to have an idea of how many we need to order so that we have a very strong probability of getting those 2 successes. Okay. So let's think our way through this. We're going to have, let's forget this 1/6 at the end here. Let's just look at this part. You've got 7 trials in which to get 1 success. What's the probability of that? That's 7 choose 1. Probability of a success is 1/6. The probability of failure is 5/6, and then raise that to the, you'd have to have 6 failures, so 5/6 to the 6th. And then the probability, and then you can multiply the probability of that happening because of independence. You can multiply the probability of that happening times the probability of the failure at the end. Sorry, the probability of the success in the 8th trial, which is 1/6. So now if you put everything together, that's, do some simplifications. That's 7 choose 1, 1/6², 5/6 to the 6th power. Okay, so that is the example of, and the development of the negative binomial random variable. I think we go on to another important random variable in the next segment. Now we consider the geometric random variable. Okay, and this is a special case of the negative binomial. And what we're interested in is how many Bernoulli trials do we require until we get that first success, right? And again, each trial is independent. The probability of success and failure remain constant. And you just keep doing your experiment until you get that first success. So repeated Bernoulli trials until you get the first success. So your K is in our notation for the negative binomial. We're looking at K is equal to 1. Okay. So let's see an example. A clinician can induce a disease in a rat with probability 0.8. What's the probability of a diseased rat in 1 attempt? Well, I just said that, 0.8. Okay. What's the probability of success on the 2nd attempt, but not on the 1st attempt? Well, the first one has to fit. Remember, these trials are independent, so we can multiply probabilities. Okay, so you'd have to get a failure with probability 0.2, and that would have to be followed by success with probability 0.8. Okay, like this. All right. What's the probability of success on the 10th attempt, but not any of the previous 9 attempts? Well, you'd have to have failure 9 times, followed by a success. So 0.2 to the power 9 times 0.8. Okay, that's a probability of that exact sequence of 9 failures followed by 1 success. Okay, now let's just generalize. We'll say that the probability is P of a success. Okay, so now if we're going to go for 9 failures and followed by success, probability of 9 failures in a row is Q to the 9, followed by the probability of a success, which is P. These events are independent of each other, so you can multiply their probabilities. So Q to the 9 times P. Okay. So what's the probability of success on trial X, but not on any of the previous X minus 1 attempts? Well, it's Q to the X minus 1 times P. Okay. So the probability of getting X minus 1 failures in a row is Q to the X minus 1, followed by success, and probability P. Okay. So basically, we've derived the geometric distribution. So the PMF for that is P times Q to the X minus 1. And we should also specify, of course, the what sort of values X can take. Okay, and now if you work out the expectation and the variance, you'll see that the expectation for this geometric random variable is 1 over P, and the variance is 1 over P squared. Okay, so here's an example. Flip a coin. What's the probability of getting a 3rd head on the 7th flip? Well, that means that in 6 attempts, you have to have 2 heads, and the 7th attempt, you have to have 1 head. So 6 choose 2, decide where those 2 heads are. There's 6 choose 2 ways of doing that. So 1/2 to the 3rd times 1/2 to the 4th. And note that the coefficient should, sorry, the powers here should add up to 7. Okay. So flip a coin. What's the probability of a 1st head on the 4th flip? Okay. Well, you have to have tail, tail, tail 3 times. So 1/2 to the 3 times an H, which is probability of 1/2 on the 4th attempt. All right. So that was the geometric random variable. Now, so far we've been going with 2 outcomes, which we can call success and failure. Now we extend that idea to you can have a possibility of more than 2 outcomes in the next discussion. Okay, now we come to the multinomial random variable. And so again, we have repeated trials. The outcomes of the trials are independent from each other, from the previous trials. And instead of having a success or failure, you could have a different number of outcomes. You could have more than 2 outcomes. So then the binomial distribution will not work. And the multinomial distribution that we're going to talk about here is in fact a special case of the binomial distribution, sorry, is a special case of the multinomial distribution that we're going to talk about here. Okay, we're going to roll 1 die. Okay, die is fair. We're going to do it 5 times. What's the probability of getting exactly this sequence? 3, 4, 2, 2, 1. Okay, probability of a 3 is 1/6. Probability of 4 is 1/6. 2 is 1/6. 2 is 1/6. 1 is 1/6. And the trials are independent, so the probabilities can simply be multiplied one after the other. So the probability of this exact sequence, how many this is 1/6 to the 5. Okay. Now, what's the probability of getting 1, 3, 1, 4, 2 2s, and 1 1 in any order? Order doesn't matter. Well, because the different orders are distinct, we can think of them as distinct events which are disjoint, right? They're mutually exclusive. If you get this sequence, then you didn't get the other sequence, right? So then we can add up the probabilities, and the probability of any given sequence, we can extrapolate. That was 1/6 to the 5. So the probability of getting, how many particular sequences are there here? So there's 1, 2, 3, 4, 5, right? So if these things were distinct, if these symbols were distinct, there'd be 5 factorial ways of doing it. But they're not. When we do that, we're overcounting by 2 factorial because there are 2 2s. Okay? So the number of ways of doing that is 5 factorial divided by 2 factorial. And for our purposes, we could say it's 5 factorial divided by 1 factorial, 1 factorial, 2 factorial, 1 factorial, times the probability of any particular sequence is 1/6 to the 5. Okay, again, the number of sequences that meet this requirement is 5 factorial divided by 1 factorial, 1 factorial, 2 factorial, 1 factorial. And you multiply that by the probability 1/6 to the 5th, which is the probability of any one of those sequences. Okay, now I'm going to start cheating. All right. The die is loaded. The probabilities are not the same. Okay, so let's say that the probability of rolling a 1 is P1, the probability of rolling a 2 is P2, the probability of rolling a 3 is P3, and so on up to the probability of rolling a 6 is a P6. What's the probability of rolling 1 3, 1 4, 2 2s, and 1 1? Well, all of those sequences, all of those possible sequences, all of those results are independent of each other, right? So we could just add up all the probabilities. So the first thing we want is to consider what's the probability of any particular sequence. Well, that would be P1 times P2 squared times P3 times P4, right? And then you have to multiply it by the number, right? So P3 to the 1, P4 to the 1, P2 squared, P1. And then the number of sequences that meet our requirement of 5 factorial divided by 1 factorial, 1 factorial, 2 factorial, 1 factorial. So then you have to add up the probabilities for all of those because they were all independent of each other. And you get this expression, right? The number of such sequences times the probability of any one of those particular sequences. Okay. It's generalizing it. Let's say we're going to have 12 rolls of the loaded die. There are n1 ones with n1 ones, n2 twos, n3 threes, n4 fours, n5 fives, and n6 sixes. Okay. So the probability of rolling n1 ones in a row is p1 to the n1, right? And then multiplied by p2 to the n2 times p3 to the n3 times p4 to the n4 times p5 to the n5 times p6 to the n6. That's for any one particular sequence, which meets that requirement. And then how many such sequences are there? Well, if all these things were independent, there would be 12 factorial. If all of these, if the symbols that you got from each row were distinct from each other, there would be like 12 factorial. But when we say that we're overcounting by n1 factorial for the ones, n2 factorial for the twos, n3 factorial for the threes, and so on. Okay. Oh, right, and we note that we must have n1 plus n2 plus n3 plus n4 plus n5 plus n6 is equal to 12. Not there's a misprint here. That should be n sub 3. Okay, so then the total number of such sequences is 12 factorial divided by n1 factorial, n2 factorial, n3 factorial, n4 factorial, n5 factorial, n6 factorial. So now we multiply the probability for any particular sequence which meets our requirement, they're all the same, times the number of such sequences. Okay. Now let's say instead of 12 factorial, instead of 12 rolls, we had capital N rolls. Then what would happen? Basically, you just have to replace your 12 by n, and your n1 plus n2 plus n3 plus n4 plus n5 plus n6 would have to add up to capital N. Okay, so this is what you get. Total number of rolls factorial divided by the multiplicities factorial of each of the symbols times the probability of any one particular sequence. Are all the same. So you add up all the you add all of these up. How many of them are there? Well, it's the number of sequences here, which is this coefficient right on the left here. Okay. So as an example, let's say we have a k-sided unfair die. So the die can roll a 1, a 2, a 3 up to a result k with a probability p1, p2, p3 up to pk. What's the probability of getting a sequence of exactly n1 ones followed by n2 twos and so on up to nkks? Well, it's p1 to the n1 times p2 to the n2 times p3 to the n3 times pk to the nk. Right. Again, we're relying on independence here. Rolls are independent, probabilities don't change from roll to roll. So this is the probability that we get. Now, if we require the sequence, if instead of requiring exactly a particular sequence, we can have these results of 1s, 2s, 3s, and 4s up to k's occurring in any order. How many ways of doing that are there? It's n factorial divided by n1 factorial and 2 factorial up to nk factorial, where n1 plus n2 plus n3 up to nk is equal to capital N. And so that's the desired probability. And now we've generalized to the multinomial random variable. Okay. So There are n trials with the same k possible outcomes each. We call those events E1, E2 up to Ek. The probabilities are of getting a 1 is of getting the first outcome is P1. The probability of getting the second outcome is P2 up to the probability of getting the kth outcome is Pk, and these are not going to change from trial to trial. Then we define random variables x1, x2 up to xk, which are the outcomes of the number of times that possible events occur. And we might use this notation on the left. I just use the one, I always use the one that's on the right. Anyway. But okay, so these are multinomial coefficients defined on the left here. Okay, so that's the number of ways of getting E1 to occur N1 times, E2 to occur N2 times, up to Ek to occur Nk times. Right, that's n factorial divided by n1 factorial divided by n2 factorial and so on up to divided by nk factorial. And then the probability is that multinomial coefficient times p1 to the n1, p2 to the n2, pk to the nk, where n1 plus n2 plus up to nk is equal to n, and of course the summation of the probabilities has to equal to 1. Okay, and we get that the expectation of xi is np sub I, and the variance of xi is np sub I times 1 minus p sub I. Okay. All right, so that was the discussion of the multinomial random